We are into chapter 13, which is called the structured groups. And the main topic here is looking at the structure of finite abelian groups. And we're going to really achieve something. So some of the times up to now, we've made remarks about the universe of groups is big, complicated, and it might be a hard problem to describe what all the possibilities are for groups of a certain size. And especially when you get into high numbers, high orders, there might be many groups of that particular order. Okay. But here in this chapter, we're going to achieve something very definite and substantial. We're going to classify all finite abelian groups. And when we say that, what we mean is we're going to come up with a description that describes like all the possible ways that finite abelian groups look up to in terms of their isomorphism process. Okay? So this is the theorem that we're going to work towards. It says every finite abelian group G is isomorphic to a direct product of cyclic groups. Okay? So we understand what cyclic groups are. Cyclic groups have particularly straightforward structure. You can think of them as they're a group of a certain size and they have a generator. They may have more than one element in the group might play the role of generator, but you can get a single element from the group, and the group just consists of all powers of that element. Once you've identified a generator of the cyclic group, the group is quite simple, really. Just the identity, it's element G squared, cubed, G4, G5, all the way up as far as G to the n minus 1. And then that gives you a list of n elements from the cyclic group. Identity, G1 through G to the power of n minus 1. It's pretty easy to look at that group and see the structure of it once you've seen what the generator is. So cyclic groups are nice. And the theorem is saying, well, any finite abelian group, remember abelian means the group operations, can be thought of as isomorphic to a direct product of a number of these. Now, what's going on with the subscripts down there? So the cyclic groups that are going to occur as the factors in the direct product. Remember, the direct product is just this construction where if you've got a bunch of groups like this, you can look at their direct product, which is the set of all tuples, set of all vectors, if you like, with one element from this group, one element from that group, etc., etc. So set of all those vectors, and this gives you a group. There's a group operation on it, Jackson component wise. Each component is using the group operations from each of those groups. So the cyclic groups that feature in the direct product are not of any old orders, but they're all of order some power of a certain prime number. So they're not just any old orders, but prime power orders. So prime power is a number that's a power of a single prime. So there'll be some bunch of primes, P1 through Pn. P1 through Pn. Now, from number theory, wherever we see a producty thing with P1 through Pn, normally the case was that the P's were all distinct. Well, here, so we're just emphasizing that they're not necessarily distinct. So you could have the same prime number appearing in multiple locations.
I have to say that that's somewhat eerily similar from something from last year in number theory.
Yeah. So what you're vaguely seeing there is the prime, where you think what it's reminding you of is the prime factorization of a given number.
Yeah.
Where you say n is equal to the product of pi to the power alpha I.
Yeah.
So this is somewhat related to that.
Okay.
Yeah. But it's not exactly.
No, it's not exactly.
Yeah. Okay. So this is quite a good result. It's a classification. Okay. Any finite abelian group is one of these. Okay? And so it's a nice example of results where we can readily understand the state. We can understand the state both at the same. Depends only on the definitions of the concepts we've done up to now. But it takes a bit of careful proving. It's not just one single thing we're going to prove in the page or something. So the proof is split up into various steps. So you've got lemmas 13.6 through 13.9. I'm going to work through each of these carefully. Now, what's the idea? So this next paragraph just gives a sketch of the proof, like a one-paragraph summary of how the proof of the theorem operates. It's proof based on the principle of induction, so it's the main kind of theme behind the motor behind the proof, the proof by induction. And the idea is to, well, since we're going to end up showing that G is a direct product of cyclic groups, what we're going to do is find some way to split off a cyclic bit out of G. So we're going to find some way to argue that any given finite abelian group, we can at least pop out one cyclic bit out of it. And we can say that G is equal to a certain cyclic group and a direct product with some other group, with the rest of the group G, so to speak, the remaining bit of G. So we're going to show, we're going to have this central idea that G can be isomorphic to the direct product of a non-trivial cyclic group here and a certain subgroup H of G. So I'm going to separate out one bit of capital G, which is a cyclic group, and then there's going to be the remainder, so to speak. And you can kind of see how the induction is going to happen, because if you can pop out a non-trivial cyclic bit, this bit will be one of these. It will be one of the chunks here, a bit left behind. But you see, the size of H will have to be strictly smaller than the size of G. Yeah, because we're breaking G down as a direct product of a non-trivial group and another group. So this group H will have to have size smaller than G. Okay. So once we get the induction going with a base case then, and we do this step, then we'll be able to imply, we'll be able to assume that the splitting of H into something like that has been done by induction. Once we show how to split off one bit, we can use that inductively to deal with a finite abelian group with any particular size. Okay. But we'll need to establish a suitable base case and prove that we can do this splitting of one cyclic bit of G. So that's just kind of like a quick pencil sketch of all these lemmas, 13.6 through to 13.9. Okay. And what you'll see appearing in the lemmas is, various bits of everything we discussed up to now. Isomorphisms, cyclic groups, factor groups. Okay. Okay. So let's get into it. So what does he say in the book here? Now we've got plenty of time for this. There's 3 weeks in the schedule. We hopefully won't need it all. Hopefully we'll have plenty of time to devote to looking at problems. So, okay. Just we'll recall some facts about cyclic groups if you've done already. We know that every group of prime order, we proved already that every group of prime order is actually isomorphic to ZP. Cyclic group order. Already proved. We also proved that if M and N are coprime, then when you do a direct product of Zm and Zn, cyclic group of size m, cyclic group of size n, it's actually isomorphic to the cyclic group of size product. Prove that result with the in the direct product chapter. And in fact, much more is true. So this is the basic result of the theorem that we've just been looking at. Every finite abelian group can be written for each pk necessarily distinct. He introduces some terminology here around generators. This result actually doesn't just apply to finite abelian groups. We can actually extend this out to what are known as finitely generated abelian groups. So we don't necessarily have to have G being finite. We can admit infinite groups into this discussion, but as long as they're finitely generated. So, okay, we already know the idea of a group with a single generator. So cyclic group generated by a single element. But we can also talk about a group being generated by a number of elements. So if you've got a group G and some set of elements, G sub I, not being very particular about what the indexing I is, but just some set of elements indexed by subscript I, then we can talk about the smallest subgroup of G that contains all the GIs. And that by definition is called the subgroup generated by the GIs. It won't be a cyclic subgroup if there's more than one of these, or if more than one of these is. But that idea, the smallest subgroup of the containing group capital G that contains all of these named elements, that's going to be the subgroup generated by those elements. Okay. And if that subgroup happens to be all of capital G, then we say that capital G is generated by those in general. So some examples that we can talk about. So we've seen already that the symmetric group S3, which is the group consisting of all permutations on 3 objects, to generate that, all you need to take is this transposition 1, 2, and this 3 cycle 1, 2, 3. By taking various products of those, you can generate all of S3. So S3 we can say is generated by these 2 elements. This group, the direct product of the integers, so the integers is the infinite cyclic group, the integers under addition. Cyclic group generated by 1. Every integer is some multiple of 1. It's a cyclic group, but it's infinite. You can have the direct product of Z with some finite cyclic, Zn. And that's certainly an infinite group. There's infinite number of choices for the first element. It's going to be an infinite group, but it is finitely generated. We only need these 2 elements from the direct product. The element 1, 0, and the element 0, 1. Every element of this can be expressed as some combination of this, okay? Because if you take a typical AB in Z cross Zn, then you can achieve that. Way. You can achieve AB. Well, firstly, you can think of it as A0 plus 0B. Yeah, for this plus is the group operation in the direct product. But then this is A times, now remember we're using additive notation for groups here. So this A times 1, 0, that just means 1, 0 plus a certain number of copies of itself, A copies of that, added together, and then plus some number of copies of 0, 1. Is, the number of those is A, the number of those is B. Okay. So any element at all from this direct product can be generated just out of taking a certain number of these elements, adding them together. This is the group operation in the direct product, and a certain number of these elements, adding them together. So we can say that this is the group generated by these 2 elements. Okay, so we can have infinite groups with a finite generating set. Okay. But the next example nicely complements that. We can also have examples of infinite groups which are not finitely generated. Infinite groups which do not, where you can find no finite set of generators. So an example of that is the rationals under addition. Okay. So the rationals we think of as fractions of integers, okay, under addition. So you can quickly do a little proof by contradiction here. Suppose that Q was finitely generated. So suppose there was some finite bunch of fractions which is going to generate every rational number under addition. Now Now we can suppose that each of these fractions, these p's and q's are not necessarily prime, but what we do assume is that each fraction is reduced as much as possible. Each fraction is written in its lowest terms. In other words, the numerator and denominator are co-primed. That's what you do when you simplify fractions as much as possible. You make the two parts co-prime. So the question is, can every rational number be expressed as some combination, some linear combination of those fractions? Well, it can't. And all we have to prove that is, well, first of all, we'll just remind ourselves of our primary school rule for adding fractions. How do we add fractions, right? P1, Pi over Qi, Pj over Qj. How do you add those together? Well, you get it as a single fraction, where you've got the common denominator, Qi times Qj, yeah, and then you've got this combination in the numerator, Pi times Qj plus Pj times Qi. Okay, so that's your familiar school rule for adding fractions. But with that in mind, so any linear combination of these fractions will just be this addition rule applied a certain number of times on a bunch of these fractions. So will this generate every rational number? Well, we can prove that that isn't so. Okay. So we need to consider this rational number, 1 over p, where p is some prime number that does not divide any of the denominators q1 through to qn. And what we're appealing to here is some facts from number theory. Number theory, we know there's an infinite number of primes, and we know that every number is factorized. You can factorize any number into a product of a certain number of primes. Yeah, it's like what we were talking about ahead of the error. Yeah. So if you just look at all the prime numbers that appear in these, and you factorize each of the denominators, you'll see a certain bunch of primes appear. So we just choose p to be a different prime. Okay. So p does not divide any of the q's. So p is some prime that doesn't appear in any of the denominators. Well, the claim is we can never express the number 1 over p as a linear combination of those. Okay? Because when you look at any operation of addition on these fractions here, the denominator that's going to appear is always going to be some product of the q's. Yeah. Now you might be able to simplify the fraction. Okay, you'll have some mad complicated numerator here. You add a load of those fractions together. You might be able to simplify the fraction, but you simplify the fraction by dividing above and below by a common factor in the numerator and the denominator. So you'll have this big original denominator here, which is a product of a load of the q's. You might be able to simplify the fraction down by knocking out some of the q's from the top of the quadrant. But what you won't ever be able to do is bring it to the form 1 over p, because p is a prime number which is not present in any of the q's. So you can't simplify this original denominator down by dividing out by certain factors of it and make it arrive at p, because p is not there to begin with. Okay, so it's a prime number that does not divide any of these. So what that argument achieves is it's saying that you can never generate all of the rational numbers from a finite generating set of rational numbers. So Q under addition is an example of an infinite group that is not finitely generated. That's just more things to be aware of. Now, okay, so I'm going to skip forward. So this here, so we've already introduced it, but here is where he introduces 13.4. This is called the fundamental theorem of finite abelian groups, the FTFAG. Sometimes we shorten it to. And we'll just look at an example of its application, see the kind of thing it does. So this is the FTFAG. So for example, remember, when you take the direct product of any bunch of groups like this, remember, This is a group which it's based on, so this is also the Cartesian product of these sets. These indexes, these powers are the sizes of these sets. And remember, the size of a Cartesian product is just the product of the sizes of the individual sets. So you can quickly say that the size of this, I'm corrupting my notes here, but the size of that set is product of the individual sizes. Yeah. Now that still isn't quite our prime factorization we talked about all the time in number theory, because remember, these PIs are not necessarily distinct. So the same prime might appear as two or more of those PIs. But you can see the connections. So for instance, let's focus on all finite groups of size 540. Okay. Now 540 has this prime factorization, 2 squared 3 cubed times 5. Now the fundamental theorem of finite abelian group says, well, any group of size 540 is going to be equal to some direct product like that. But these subscripts have to have this property that when you multiply them all together, you get the size of the whole thing. So they're going to be things looking like this, but they must have the property that when you multiply them together, multiply all these sizes of the individual cyclic groups, they must come to 500. 540 has that prime factorization. So we can quickly just list down all the possible examples of this kind of construction that have size 540. And we can quickly see a not too big list. There's just one more at the top of the following page. So 1, 2, 3, 4, 5. Let's write it down there. 4, 27, 5. 4, Z27. It's the last. That's the last one at the top of the following page. So there's just 1, 2, 3, 4, 5, 6 possible isomorphism classes for groups of size 500. You'll notice in each of these, product of all the individual sizes always comes to 540. So we've just got various ways of taking this factorization of 540 and spreading out, or not, the various factors and arranging various constructions like this. So we can either consider each of the prime numbers on its own. So we got Z2, Z2, Z3, 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 and Z5. So 2 2s, 3 3s, and a 5. And we have that direct product. Or we might choose to take two of those, take that, those two copies of Z3, and instead of the direct product of those two cyclic groups, get a so that the direct product of those two is size 9. We'll get a different cyclic. We'll get a different group of size 9. Cyclic group of size 9. A different group to Z3 cross Z3. And the rest of the construction is the same, Z2, Z2, Z3, Z5, and Z9. And just various ways of doing the combinations, okay? Just gives us those six possibilities. Each of those 6 are different isomorphically, and there's no other way of writing down a group of this type of construction that will have size 540. That is in a different isomorphism class to the. Now, you could write down, strictly speaking, a different group in a kind of a trivial or a strictly speaking, a different group, but not a different isomorphism. For instance, let's look at this one down at the bottom. We could choose to swap the positions of Z4 and Z5. We could make the first entry in the direct product Z5 and the last entry Z4. It'd be a different group. The elements in it are different. The vectors in it will be different. The first components of this one have something from Z4 in the first position. Whereas the first components in the other one would have something from Z5. But those two, while they're different groups, they would be isomorphic. It's just the mapping from one to the other that swaps those components of the vector, that would be an isomorphism. So that's just been an introduction to the result itself, looking at kind of one example of laying it out. So this answers, like, before we saw this, we didn't really have any way of capturing, how many different Abelian groups are there of size 540. When it was pretty big, we might have thought there was, how many really essentially different examples of Abelian groups of size 540 are. Well, with the aid of this theorem, and once we prove this, what we'll be able to say for definite is, well, there's only 6 possibilities. These 6. These are representatives of each of the isomorphism classes. Any finite Abelian group of 540, size 540, will be isomorphic to one of these. That's the strength of the result. That's what the result is saying. Okay, I think we can talk our way through this one as a first step. So this is the first lemma going towards this. So we've got a bit of terminology here, which is talking about P groups. So a P group is a group where every element in the group has order some power of P. In a P group, it might have elements of different order. But all the elements, their orders are always some power of the prime P. So that's what's called a P. So that's going to feature in the discussion throughout this chapter. Okay, so this first lemma is our first step on the way. It kind of, remember Lagrange's theorem said finite group of a certain size, if there's a subgroup of the group, its order must divide the size of the group. That's what Lagrange's theorem said. This goes somewhat in the other direction. Because if you start off with a big group, and we can pick out a prime P that divides the order of the group, then this says that G does contain an element of order P. Well, if it has an element of order P, that means it'll have a cyclic subgroup generated by that element, size P. So this is going in the kind of opposite direction to Lagrange's theorem. Picking out a certain divisor of the size of the group, prime divisor, and it says that the group will have a subgroup of that size. Remember, that's when we first talked about Lagrange's theorem, we said, well, you have to be careful. Lagrange's theorem doesn't say there is a subgroup for every divisor of size of the group. Cautioned against that. And our example of A5 or something, 5 had no subgroup of order 12, or was it A4 or 6? Yeah.
If A4, 6 didn't exist.
Yes, there's no subgroup of order 6
Yeah.
in A4, 5. Yeah, but this is saying, this is asserting something positive in that style. For prime divisors, 6 is not prime, of course. Yeah, but for prime divisors of the size of the group, we'll find cyclic subgroups of that prime size. Yeah.
So wouldn't that imply that P divides G?
P divides the size of G.
Yeah.
Yeah, but that's the way it's introduced. It says if P is a prime that divides N, or N,
then,
N is the order of G. So yeah, so Lagrange's theorem tells you that this P, if there's a cyclic subgroup of size P within G, then P must divide size.
That's where I was talking about.
But the logic here is going in the opposite
direction.
You start off, you say, P divides the size of G. Therefore, I know there's within G somewhere there's a cyclic subgroup of size. That's what this means.
Right.
I kind of want to do it justice and maybe not squeeze it into the remaining 9 minutes. I think I won't. I think I'll save it to tomorrow actually, because I just want to, because it's there's just 13.6, 13.7, 13.8, and then 13.9. I don't want to speed through that. So I'd rather start off next time patiently laying that out, because it is a really nice argument. It works by induction. You see that, because it says it at the start. And it has a base case, n equals 1, which is trivial, so there's nothing to prove. Because what's the group of size 1?
4.
Yeah,
Boring. Are there any primes dividing it?
Or just 4, 1. Oh, the one's not right. I always do that.
Yeah.
Always do that.
So there aren't any p's
No.
dividing it. So there is literally nothing to prove, nothing to show. It's vacuous. So the theorem is vacuously true for groups of size 1. And then you go to the induction step. Now the induction step looks, so that's, we've declared induction. The base case is not proved, so the whole rest of it is just doing the inductive step. And you can see in there we're talking about factor groups. So that's quite interesting. So we're using factor groups in the middle of this induction. You can read ahead of it if you want, but we'll work through all details of that tomorrow afternoon. But what we could finish on is going back to this here. So these are all our finite abelian groups of size 540. But there are typically two different ways of viewing them. This is viewing them spread out as much as possible into direct products. But remember now, we introduced it at the front. Remember, we have this result that if the GCD of M and N is 1, that implies that Zn, the direct product with Zn, is isomorphic to Zn times n. Okay. So if we apply this result as much as we can through here, we get in some senses, a better, more compact description of these. Okay. This is an example of it down here. See. 4, 27, and 5 are all co-prime to one another. So this is actually isomorphic to Z 540. Maybe somebody should have said at the start, hang on a minute, cyclic group, abelian groups of size 540, surely Z 540 is one of those. So we should have maybe asked ourselves where on this list was Z 540. Well, it's here, it's the last one. And what I'm going to do to each of these examples, I'm going to apply this result as much as possible. I'm going to look at these and see which factors of here I can package up together. And keep doing that as much as possible. And here they're all spread out. So the biggest thing I can form here is if I take the Z5, one of the Z3s, and one of the Z2s, and put them together, and that'll be 5 by 3 is 15, so by 2 is Z30. So there's a Z30. Now Z30 deals with one of the Z5s, the Z3, and the Z2. So then remaining, I've got another one of the Z3s and the other Z2 I can put into a Z6. And then there's one more Z3. So this first possibility, you can also think of it as Z30 cross Z6 cross Z3. Product of those three is 500.
180 times 3.
Is that 540?
Yeah.
I'm sorry.
Yeah, 100%.
Doubting myself there. So what's this next one? Well, here I can take the 5, the 9, and the 2. 5 by 9 is 45, and by 2 is Z90. And then what's remaining? The Z3, the other Z2, Z6. Here I can take the 5 and the 27 and the Z2, so that's Z100, 3, was it 270 plus Z2. This one is also isomorphic to, so what can I do here? I can do the 5, the 3, and the 4. 5 by 6, 60. So this is, oh no, I haven't had one 3 transits. That's the 5, the 4, and one of the 3s. And then I've just got, well, you see, I can't multiply together the 2 3s, so I'll have to leave those as 2 separate Z3s. What you don't say is that that's isomorphic to Z9.
Mm-hmm.
No. because that violates this. The last possibility, I can take Z5, Z9, Z4, so it's 20, Z9, Z 180. It's just a Z3. So this is just an alternative way of looking at it. Okay, so this is not the way that the theorem is expressed. Remember, the theorem says, the theorem kind of declares the standard form for these finite abelian groups is a direct product of cyclic groups, each of which has prime power order. Okay, well, that's not the representation we're using here because we have lots of non-prime numbers. But it's just another alternative way where you make the direct products as short as possible. This way makes the direct products as long as possible. None of these can you split up anymore. And you can't break down that Z27 into Z3 times Z9 because 3 and the 9 are not co-prime, so you can't make use of this. So these representations are where you're using a direct product as long as possible. This representation is where you're using a direct product as short as possible. That's one way you can think of these two descriptions. So you've got a division here. On the left, we've got as long as possible. And on the right-hand side, we've got as short as possible. Short as possible, a way of representing that isomorphism class of groups of size 500. Okay, there's still 6 possibilities. And we can see Z540 itself here now as that last one. So it's just another alternative way. So some books that you read, they might quote the result in kind of using this representation. And indeed, I think those are called the torsion. I think those are called the torsion coefficients. I think if you look that up. So the torsion coefficients of a finite abelian group is this set of numbers, which represent the isomorphism class. So a group in this isomorphism class would have the torsion coefficients 217 and 2. Okay, so that's a good place to finish today. So our task ahead of us now is to build up to the proof of 13.4. Okay. The one paragraph summary of the idea of it is there in that second last paragraph there. That's what these various lemmas take us through this path. Okay? Good.